this is how it's going to look. We have the first step, a conventional reactor, using about 20 to 25 days retention time. Then the effluent from the first reactor going to sedimentation. Probably we need to use some polymers. We will have a separation of phases. The solid phase that we will treat it with lime, and going into the second reactor, in which we'll be applying between 50 or 100 days retention time. We don't know yet how much. So, what are our specific objectives then in this project? So the specific objectives on the project is to make a laboratory scale study in which we will study phase separation, sedimentation with polymers, and we will also try this alkaline treatment with lime, alkaline treatment of the concentrated manure, and see which effects they have in the gas production and mineralization of nitrogen. How to proceed then at lab scale? Well, the first step at lab scale then is also how to set up a lab reactor. Here we have two reactors, 35 liters each, and they are running at 37 degrees mesophilic with an organic loading of 3 grams BS per liter per day, a retention of time of 25 days. We started the reactor with an inoculum from Groningen, based mainly on manure, and we are loading it with liquid manure that is coming from Alunda, outside Uppsala. As you see by the TS, and the liquid manure from Alunda has a very high dry matter. It's very rich in straw, and the methane production that we are having from these reactors is 140 liters. Oh, it should be kilos BS. It's not grams. Kilos BS. So it's a rather normal production, probably within the lower range. There are different methane production or calculations of from manure. Normally, it could be said that we can be producing 200 liters methane per kilo BS, but here we have a large amount of straw. So this is a normal production of methane from this substrate. The next step is sedimentation, but before we get into sedimentation, we needed to know which type of polymer we are going to use. So we did a polymer screening. Polymer, of course, compounds that are being used to aid or to facilitate the separation of phases. And there are several types of polymers, and they can be classified depending on different aspects. The charge, for example, they can be cationic or anionic. The charge density can be low, middle, or high charge. They can have also different molecular size, low, middle, and high molecular size. And the structure also can be different. They can have linear structures or they can have branched structures. We can have also synthetic polymers and natural polymers, the ones, for example, that are the starch-based polymers. So what we did is to make an evaluation and to study the effect of the polymer concentration on the structuring of digested material. We make a rough screening of all of these polymers, and what we did is that we took the manure, the same amount in all cases, and we mixed it with different amounts of polymer solution, and then we filtrated the mixture through a nylon net and measured the volume and the weight and the TS and BS. I'm just going to report the volumes of the filter, and we got different types of figures here. For example, The Aquafloc, it's a starch-based polymer, didn't give any effect. No differences compared to the control without polymer. Then we got these some figures as the C498, giving a very sharp and very narrow behavior, which is probably not so good if we have the substrate that is changing in the organic composition. In the case of high molecular weight polymers, the one in the left corner, we have a very narrow behavior also, but also a negative effect of the polymer. So it was producing during certain concentrations less filtrate than the control. And the one that gave the most robust behavior was the C448, which is a low molecular weight with high charge and linear structure. That means that with small concentrations or small amounts of polymer, we get good filtrate, and the same filtrate volume can be kept at larger concentrations.